Okay, so we got the doors open again. That's all right. When Charles stands up. Welcome, I'm Persis Drell. I'm the Dean of the School of Engineering, and I'm delighted to see all of you here tonight. We're here to honor Charles Simonyi, the co-creator of the first WYSIWYG, text editor and chief architect of Word, Excel, and other programs that we all use today. I just have to say about the acronym WYSIWYG, I'm from physics, and we really pride ourselves in our acronyms. And we don't have anything that comes anywhere near close to WYSIWYG. So I want to say a few words about the Engineering Heroes program that we have here at Stanford. It was created in 2010, and it recognizes the achievements of Stanford engineers who have advanced social progress, economic progress, improved the human condition, and it's really an opportunity for us to celebrate the profession and really inspire the next generation. Along with Charles, this year's inductees were Andy Akravos, a renowned chemical engineer, and Ted Hoff, the architect of the first microprocessor. These three newest heroes join a very distinguished group that includes Fred Terman, Vince Cerf, Sally Ride, the founders of both Yahoo and Google, and Martin Hellman, who is got named a hero for his work in public key cryptography and is here with us tonight. Welcome. So, unlike many award events, the only thing we ask of our honorees is to tell us how they'd like to spend some time on campus. So immediately before this lecture, Charles had a fun conversation with a small group of students, and then he also suggested tonight's talk with the rather provocative title of Memories of Future and Space, and you're going to learn what that's all about in a few moments. But I'm going to tell you a little bit about Charles first. So in 1972, Charles was pursuing his PhD in computer science here at Stanford and working at Xerox PARC, which was really in its heyday as an innovation powerhouse. And at PARC, he began to work on what became known as the first What You See Is What You Get text editor, dubbed Bravo. Before Bravo, even the very simple task of formatting a document for print or setting a typeface, text size, making text bold or italic required that you had to code. And even when you knew how to do that, what you saw on the screen really didn't give you any indication of how your document would look. And I think anyone in the audience under the age of 55 has no clue of what that world was like. Just no clue. Thanks to Charles, you have no clue of what that world was like. But thanks to Charles's work, what people see on their monitors now looks like what it resembles in print. So rather than have to learn a markup language, users actually can format a document simply by looking at it. So in 1981, Charles joined Microsoft as its first director of application development, chief architect, and distinguished engineer. We were talking over dinner about what an incredibly bold move that was to leave a secure job at this great Xerox PARC and go up to this unknown place up in Seattle, working for these unknown people up there. He was employee number 43 at Microsoft, and he spent 21 years there, and he helped shape the way we work today. He was chief architect of Word and Excel, and then presided over much of the Microsoft Office application suite. He left Microsoft in 2002 to found Intentional Software, which is delivering software for the new generation of large wall-mounted displays that are touch-sensitive. That was the first part of his career. And then he took up what I guess was really a passion from childhood, and got involved and has achieved quite a bit of note as a space traveler. Apparently his interest in space began as a child in Hungary when he received a book called Battle for Speed about space. I went on Amazon last night to look it up, and I couldn't find it. Okay.
It's a Soviet book.
It's a Soviet book, okay? Amazon has not penetrated that market yet. But I did look. At 13, he won the title of Hungary's junior astronaut and got to travel to Moscow to read a real cosmonaut, Pavel Popovich. He was able to travel in space in 2007 when he became the 5th person to go to space as a tourist, and he's actually twice traveled aboard the Soyuz and visited the International Space Station, logging a total of 28 days in space. And actually he's the first tourist who's gone twice. He's also a pilot with more than 2,000 hours of flight time with licenses to fly on both jets and helicopters. And I meant to ask you over dinner if they ever let you at the controls of the Soyuz.
Yes.
Yes. Okay. I'm somehow not surprised. In addition to all of those achievements, he's a member of the U.S. National Academy of Engineering, the American Academy of Arts and Sciences, a corresponding member of the Hungarian Academy of Sciences, and chairman of the Board of Trustees of the Institute for Advanced Studies at Princeton. He has a bachelor's in engineering mathematics from UC Berkeley and a PhD in computer science from Stanford. Tonight we are celebrating Charles as a Stanford Engineering Hero, and we're honoring him with a token of our admiration. If you would come up here, please. And I will present you with a token, which you may keep, with a picture of you.
Laser etched.
Laser etched, I think.
Yes.
Which you can show. And if you will join me in recognizing Charles as a hero. And maybe I'll hold that.
Yes, please.
Because we are now going to ask him to tell us what it means, memories of future and space. Thank you very much.
Thank you, Dean Drell. I'm so pleased to be here, and I think this recognition is so touching. I'm in a company that of my heroes, and I don't know what I've done to deserve it. And I did a multivariate analysis of what do these people have in common besides being related to Stanford, and I found that most of them, but not all of them, have been born a long time ago. So, and I'm not using the synonym for that because I don't feel that way. I don't feel old. But I was born a fairly long time ago, and I want to share with you some of those experiences that I had. Now, the members of future and space, the space is self-explanatory, but everybody wants to know about the future. We all want to be oracles. If in all the examples in philosophy or in business especially, I guess it's the oracle is the highest aspiration level, and it's very hard to be an oracle. On the other hand, you can look backwards and look at how the future looked in the past, and of course, there's no guarantee that this will be repeated. As they say in the financial business, the past performance is not necessarily indicative of future results. But still, I think it's an interesting trip down memory lane, and I hope that I will show you some past interesting documents that you may not have seen before, and you will find entertaining. So I will have two parts to the talk. I will talk computers first, and then I will talk about space next, since it's of interest to many of you. Usually I don't start talking about space, but when people ask me about it, I think that it's with the space flight is such a privilege, and with this privilege comes the obligation to share the experience. So I'm just very happy to share those with you. And this is before I was born. We are talking about 1945. This is a meeting at the Institute for Advanced Study, and if you ask historians when computers were invented, you will get, understandably, many different answers. Why? Because it depends on how you define computer. But there's a particular pattern for computer architecture called the stored program computer. And this particular pattern is since have been repeated in practically all the computers we use today. It's called the von Neumann architecture. And you notice that von Neumann is there, and there's actually a block diagram, simple block diagram of the stored program computer, and many other famous names there. But von Neumann, here is von Neumann standing in front of the first stored program computer, IS computer at the Institute for Advanced Study. He told one of his colleagues, he has been working on the bomb during the war, and he told one of his colleagues, I'm working on something much more important than bombs. I'm working on computers. The interesting thing about this, and the way I'm connecting it up with the rest of the talk, is that this design was published. It wasn't. It was put in the public domain. There was no patent, and since it was put into the public domain, it was copied in many places on the world. And in particular, I'd like to bring to your attention the fourth one, BESM, and the fifth one, Dask. So it's Russia and Denmark copied this machine. So why am I mentioning this? Because this is the grandson of the IS computer called Ural-2. And this is the computer, this is my first computer. Okay, this is it's unbelievable. In 1964, when I managed to get machine time on this machine, and I after a very long evening with a terrible headache, I calculated I think it was a 30 by 30 magic square. So it was very successful. Now the interesting thing is that it's a first generation computer. It runs on vacuum tubes. It has no operating system. That means that only one person can use it. So let's remember that. One person can use it. And how fast is it? It can do instruction about every 100 microseconds. That's 10,000 instructions a second. It's a very pleasant speed because it's in the audio range. So you could hear it. You could hear the modulated execution of the code. It doesn't last long, but it was beautiful while it lasted. So I could tell you so much about this machine. In particular, here's the code of one of the first programs I wrote. It's in octal absolute. Notice all the sevens, now no eights, nines. So it's in octal language. It's wasn't printed then. It was printed at Xerox much later from a simulator. We didn't have a printer. Russian machines, they didn't have mechanical parts. So we couldn't print it. We all worked from handwritten notes. But later on, I could read the paper tape and printed it out for my own posterity. So then next year, I graduated very quickly to the second generation computers. This is a typical second generation computer made in Denmark. The grandson, again, of IES. I didn't know it at the time. And I just assumed that every computer had 40 bits word length. So the familiarity got lost in all the details. So it just so happens that my first two computers were related so closely to each other. Notice that it's in Danish modern design, and even today, when I smell teak oil, I'm thinking of this computer. Now, this is this is code. The code got much more complicated. It's incredibly optimized machine code on the left, and so complicated that we had to write our comments in high-level language to explain what the code was doing. So that was the way of doing comments. Notice that the high-level language is quite familiar. We'll return to that. And you might ask, with all that effort and genius that went into, this is not my code, so I can say that, the genius that went into optimizing the code, how much better it is than code today. And I measured it very carefully. It's about 5 times better. Now, you might say 5 times is nothing. So, because the effort is practically infinite. And 5 times is a couple of months in Moore's law. So but at that time, that was very, very significant. So that's the second generation machine. The next year, 67, I arrived to Berkeley, having saved money in Denmark, and I'm graduated to the third generation of computers. This is a typical first third generation machine, the CDC 6400, that was running at Berkeley. Many of you know it, and so on and so forth. So notice that there was this time warp. I think it's a fairly unusual arc that I had the privilege of experiencing, of going through and working actively on working computers of 3 different generations over 3 years. So, but this wasn't, this lasted for a while. It paid for my non-resident tuition at Berkeley. And during working on this, I met some professors. I joined a company called Berkeley Computer Corporation that went bankrupt, which was the bad news. The good news is that the professors were moved en masse to Xerox. And they took me with them because I was useful, I think. So, I mean, at that time, I didn't even have my Berkeley degree, the undergraduate degree. But anyway, they took me. And also, I didn't have work permit, but other little details. So, at Xerox, I ran into this guy, Alan Kay, whom many of you know, and he was advancing this idea. Actually, he was advancing it earlier in '68, but this is from a publication in '72, and that's when I saw him, the Dynabook. That will be the future, and here you see it, and he had a paper model of it, and he was showing it to me and telling me how this is going to be the future, and one day a PDP, this will have a power of a PDP-10. So I said, I don't know if I believe that it's going to be a PDP-10, but I definitely don't believe the flat display. That's right out. That's now the good news is that Alan inspired a lot of people at Xerox, and they came up with what Alan called the interim Dynabook. So this is the interim. Before we get all that goodies, let's just have a machine like this that fits under a desk. In fact, we had to give names to our machines because they were on Ethernet, and they were connected to a laser printer. And so one of our colleagues, John Allenby, called his machine Gazunda. I asked him, John, why do you call it Gazunda? He said, because it goes under the desk. And you can see the disk drives, the floppy disk of that time. They have enormous capacity. I'm not going to say how much it is because I don't remember, but it was 1 megabyte or 5 or whatever. But thank you. Thanks very much. Yeah, lots of Alto people here, and but you can see that it has some significant features. It has a landscape-oriented display. It's black and white display, and it's a bitmap display, which was a tremendous advance. And you could immediately see the degrees of freedom that a bitmap display offered that was unlike anything before the 64, the first, the second, the third generation, whatever. So this was something brand new, and it also had a pointing device, the mouse, that of course you needed to address the bits on the individual bits on the screen. So this was a fantastic experience, and we exploited this experience by creating software for word processing called Bravo, and I'm just so glad that two of my colleagues, Larry Tessler and Tom Malloy, that both worked on various aspects of the user interface and the system code in Bravo, are here with us. And as you see, it was actually quite a nice program. Notice the dotted tabs. For example, that's a nice feature, don't you think? The table, but the other interesting thing is if you actually read it just happens that this is an example document. It's a price list. Okay, the second column is price in dollars, and let's just see some of these dollars here. You can get a high-speed printer. This is a laser printer for 156. Am I right? Something $150,000. Okay, that's your laser printer, and then you can get a the gateway was a file server with 300 megabytes of memory. It's only $123,000. So as you see, the prices were quite intensive, and it was maybe a bit ahead of its time, but it certainly showed the future direction. The alternative direction was the personal computer. And this is the first personal computer I saw, and I think that actually it was Larry Tesler who brought it in. Am I? Yeah, Larry's here. So he brought this in, and I almost burst laughing when I saw this comical machine. And our stuff was so much better. But not much later, somebody showed me WYSIWYG running on a machine with the same performance, and I realized that wait a minute, the people will be able to do at a very small fraction of the price the price point that we have established, stuff that is very, very useful. Maybe not as pretty, but incredibly useful. So that made me rethink my thoughts, and that's what, as the Dean mentioned, that I went to met Bill Gates in 1981, and we had a great time, and rode this path, instead of jumping forward, we rode the organic path of growth from the bottom up. Now, the interesting thing is, as I mentioned earlier, the idea of a personal computer, it wasn't foreign to me, because I always thought that the machine was personal. You know, even at Berkeley, when I got the machine, it was mine. You know, I was a systems programmer. I could break it. I didn't respect the operating system. So the personal computer was one thing, but the performance, you know, this idea of having a limited performance, which, trust me, the early machines certainly did. That was familiar to me too, and I knew what it took to do those calculations. Not many of my colleagues had the experience. They were either super young and they didn't know it better, but they didn't have experience, which was kind of a plus. Or they were older, but they haven't been so old as I, namely having worked with first-generation machine. That's when people who used first-generation machine in the US started to die off. Because, you know, they had the middle of their career in 1945. So, and I was at the very beginning of mine in 1966. So this made a tremendous difference, and so that was the lucky streak at Microsoft, and of course we got to where the Alto was for the first time in 1984 with the Macintosh. And the Macintosh was Alan Kay, again, his inimitable style. He said it's the first computer good enough to criticize. Now, I'm not going to bore you with the details after 1984. It's you probably have seen all these computers got better and better and more bits and so on and so forth. You might ask what's coming in the future. All I can say is that watch out for large wall-mounted multi-touch displays. I think that they are coming, and you will have many of them here and everywhere. It's this is an open area, you know. Everybody has multi-touch on their phones. Everyone has multi-touch on their pads, or whatever, the little computers, tablets, right. The X-pads. But the multi-touch in the wall is still awaiting, and it's going to be a big thing. Now, just to combine all of these experiences, I have to say that the state of programming from 1963 to 2015 is not that different. And here I have an example. This is an actual program. It's not made up. It's from because I found it in October 1963, has a comment in the front of it. And in some respects, the one on the left, written Algo 60, looks better than one on the right that is in one of the modern languages. I know there's lots of advantages, and we have all kinds of wonderful things, and I'm super grateful for it. But it's not the kind of improvement that we saw in hardware and with Moore's law. And let me illustrate what Moore's law brought us. And this is a page from Heinlein's book, Moon is a Harsh Mistress, and we'll see that later in the space portion of the talk. But anyway, the story here is that Mike is an artificially intelligent computer, and the man is the creator, and they are talking to each other, which is irrelevant to our, but basically the man is asking him for some memory that he can use for his own notes, the man. And the computer, of course, obliges because he's a good friend of the man, and says, yes, man, I have an empty memory bank, 10 to the 8th bit capacity. Now, 10 to the 8th bit is roughly 10 megabytes. 10 to the 8 is 100 million, but let's say 10 bits per byte is 10 megabytes. You can get basically 1,000 times that much. Sorry, right. 10 gigabytes you can get for $6 on Amazon. So he is basically giving him 1/6 of 1 cent worth of memory. So he's not very generous. And considering that he's artificial intelligence and the moon this is in 2020, by the way, I think it's an underestimation, which is kind of interesting that this was the fantasy. He had to write the maximum that he could think of without sounding ridiculous. And so he did 10 to the 8. Now here's another piece of, this is from Fred Brooks' book, The Mythical Man Month, which is still read. It's reprinted because it's mostly about software. Whatever he writes about software is still true. And just randomly, you find this line. It says that on a Model 165, now this is a 360 or whatever, 370 by that time, Model 165, one of IBM's wonderful machines. This is the same time as the Alto, remember? At that time, memory rents for about $12 per kilobyte per month. Okay, now remember that, $12 per kilobyte per month. Okay, so $12 a month gives you a cash flow of $144 per year per kilobyte. Let's capitalize it, say, at $2,000. That's reasonable cash flow, business students, right? So let's make it 5K today's dollars, because this was at then dollars, okay? So, which means that it gives us a valuation of $5 billion per gigabyte of capital costs, and that means that it's $300 billion for 64 gigabytes. Okay, now, I can go to Amazon, and for $30, I get this piece of memory. So that's 10 billion times better than what it was. I mean, that's really incredible. I mean, that's what the real Stanford Engineering Heroes did. So let's see the space angle for all this. This is me in 1963. I was kind of excited about space. I did this TV quiz. I won it. They went to Moscow. And I was really into space, and it really motivated me to learn English, so that I can read about the American space program. And that's how I learned English. Well, then I discovered computers, and the whole thing went wayside. The computers were much more practical and immediate and tangible and so on and so forth. So nothing happened after that. But because we are talking about the future, let's see what the future looked in the past. And in 1968, in San Francisco, I remember when it was either the premiere of Space Odyssey, and I saw it, and I did a couple of pictures. Say, first of all, this is how the space station should have looked in 2001, and I want you to remember this picture. It's kind of interesting. It's a very nice interior. The panels with documentation. That's pretty good, don't you think? That the documentations were obviously on computers. So that's pretty good. The next one, another interior. This is the other interesting thing I found was that there's a Hilton is in space. That means that commercial space was kind of predicted. That's okay. The other interesting thing is that these people here are supposed to be Russians, of course. They are Russians. But actually they are not Russians. It's made very clear that they are Soviets. And it's true that Russians are space today, but Soviets are not. And again, another thing that science fiction didn't predict the collapse of the Soviet Union. So now this is the zero gravity toilet, a famous picture, and here's a close-up of the instructions. I want you to remember this. Not just the shape of it, not the details. Don't worry, there's no quiz. I have had a quiz, but there's no quiz on that today. But I tell you, this one is I remember this distinctly, that it made me very excited. This is a cockpit of a craft, obviously a spacecraft in this case. There are two pilots, and there are these visual displays in between. Now, with science fiction movies, you can always tell when they were made because they used the best graphics available at the time. Well, at this time, there were no graphics available for practical purposes at all. So, which is very lucky because they used, obviously they used animation and drawn animation to make displays that were very, very interesting. Very interesting and functional. And how functional were they? Also notice that there's no steering device, but they're probably using side stick controllers. So here's a picture of a modern jet, and actually in flight. And there's no side stick controller. It's almost indistinguishable from the other picture. The two people side by side. Side stick controller displays that are showing very interesting stuff. By the way, here, this is called what is called, not virtual view, synthetic, oh right, synthetic view of the terrain under you. So it works, it's a complete independent system that simply has the complete map of the world, and GPS tells you where you are, and it knows what direction you're looking at. It's a virtual reality of the world under you, but it's precise enough so that you can navigate and land the plane using the synthetic view. This is, I think that this is very compelling, and it's a great. Now, here's another disc you have never seen before. This is an actual slideshow that was presented by Werner von Braun just a couple of months. If you remember, July was of that year was the first moon landing, and of course, you know, the big promise to President Kennedy that decided that this goal was the best way to organize and measure the best of our abilities and skills. That came to be true in a large part to the efforts of Werner von Braun, whose rocket, you know, worked flawlessly or practically flawlessly, and in an incredible gutsy. So Werner, what was Werner doing at the time? Well, you know, he didn't have to do much with the rockets anymore. He was planning a Mars mission, and he presented this. He wanted to present it to the president. He didn't get very far, but I have the slides. Very professionally made. This is the plan. Notice the date, 1981. Okay, if he had gotten the go ahead, he would have done it. I'm convinced. He had done the moon mission. He would have done the Mars mission. There are 120 slides here. Obviously a lot of work went into it, and it sounds very reasonable. Notice that there's a Venus swing by to come back, and so on and so forth. This is the details of the plan. I'm just showing the highlights, and this is the percentage of GMP that would have to be spent for it, which is actually it's you know. Well, it's not too bad in a sense that you look at like in 1964 it was very high. It stays well below the 1969. Well, actually not that much below, but it stays in the same neighborhood. It's a little bit cheating because he talks about the percentage of the GMP, not the percentage of the budget. You know, there's a factor of 10 at least at that time. Probably it's a factor of 3 now. But so anyway, it's a sleight of hand. But still, it's interesting. It's comparing it with the historical data. Remember, here, this is where we are now. This is 69, if you can see that. So it's a very interesting thing. And he basically said, "Hey, just give me the green light. I'm going to take you to Mars." And it's pretty interesting. Why didn't it happen? Well, of course, nobody listened to him. It probably didn't make much sense. The actual growth in the GMP was a little bit less than 4%. This is the actual growth of GMP, and I drew the line at 4%, just that you see it never reached 4%. It would have been pretty expensive. There would have been some failures in his program, although there were failures in the Apollo program too. But also, I think that the goal wasn't that clear, and frankly, it's not that clear today either, of why go to Mars. It's no longer the organize and measure the best of our abilities and skills. Now we have other ways of doing that, it seems. Anyway, so just I thought I'd share this with you, and this leads us to 207 and 209 private space flights, which was a kind of an incredible opportunity. Nobody expected that private people would go to space. Just like it was, again, if you look at Star Trek, you know, everybody's wearing uniforms. You know, everybody came from Starfleet Academy. You don't see too many you know, people with the right stuff went to space. What about the rest of us? and in a way, you know, what are we doing in space anyway? People say that well, we need to find out how the human body reacts to space flight. Great. Well, I have a body, and in fact, I have you will get a better distribution if you take my body as well as, and in fact, some scholarly papers have been published. I have PVCs, preventricular contractions. And nobody went with PVCs to space before, so there's a nice paper on space flight with PVCs, and which is okay. And I had a EKG in space and other things. So I think that it's better to have a larger sample of people and a greater variety of people going to space. If you want medicine, if you want science, I think that you should send probes, and they do a much better. The main thing is not to starve the science people with the human space flight budget. But of course, if people want to pay for it, that's a different story. Then it becomes a commercial proposition, and that one is self-sustaining and self-correcting. So anyway, here I am learning Russian. It's a lot of fun. I'm wearing a scarf because it's cold. In the classroom. This is the rocket, the Soyuz rocket. In comparison with the shuttle, you can see it has much less payload, but it does the job, and it was designed in the 60s. And this is what I guess von Braun was saying too, is that, hey, we have this Saturn V, we can just tweak it here, tweak it there, just continue turning the crank, we can do all that. Well, the Russians have been turning the crank on this booster here, and it's still flying. The shuttle is, as you know, is not flying anymore. The bad news is that NASA, of course, needs all the seats, so the prices went way up. So there's no third flight, and actually has not been tourists pretty much. There was one quickie tourist right after me that was kind of done very quickly without training because there was no time. There was a change in plans and somebody had to jump in. But no tourists since then. So this is the spacecraft. It has 3 parts. The return compartment is in the middle and the living compartment is on the top. So it's quite comfortable. Spacecraft in real life, the first time I saw it. And here's me with the crew right in front of it after a training exercise. And this is how the rocket looks couple of days before launch. It's quite a routine operation. It's incredibly robust system. It's in a rail car. We are 2 days from launch, and everything is fine. You know, people are around it, and then comes a big locomotive and pulls it out to the pad. They erect it, they fuel it, and off you go. And all right, these are all the different parts that you drop at different times. And fortunately, it's all documented very carefully. This is Russian documentation, but it flies wonderfully and reliably and robustly. And notice also the angle. It's pretty much from below, so it was done from a insanely. This picture was taken by my brother, and he was standing insanely close to it. This is the acceleration graph. It's not as rude as you would think. Notice that it starts at 1 g at launch. It's nothing dramatic. It's full of fuel. It's kind of gets off like an elevator. You feel like you're in an elevator. Then of course it kind of peaks a little bit, and then peaks twice more. This is finally we are in space. There are all kinds of interesting things about space. My crewmates, we are pretty close to each other. And notice that everybody's red in the face. That's typical when you arrive to face. Your heart is still pumping blood as if it were going against gravity. So it pumps blood harder into your head. And that creates a condition called space adaptation sickness, and half the people get it and get pretty sick. Now, I was just going to mention, because this is part of our checklist, and notice that all the numbers are octal. So this is still octal numbers, and there are the addresses, octal addresses, and the octal words in those cells that we are supposed to check to make sure that everything is hanky-dory. These are still the 1960s computer that are running. There's actually a display that is run in a 386. They use a 386 because it's more radiation resistant, and we are talking here space radiation. But it's just simulating an earlier hardware display and to save weight. So everything is the same, and the computer is just doing the simulation of the hardware displays, but it's not participating in the actual operation of the spacecraft. But this is the computer that controls the spacecraft, and it's our checklist. It's another good news. The checklist is prepared in Microsoft Word, and they did a fantastic job. I mean, Okay, so we have to include a picture of the Earth as you're going around. There's a lot of clouds and a lot of water, that's for sure. And this is the living room. I just wanted to point out this quaint manometer that measures the air pressure. And it also can be used to measure other pressures. It's a vacuum manometer, so it goes down to 0. But it's completely mechanical and has no electrical components, so it cannot possibly fail. And that's the robustness of the system. Some of the systems are from the 19th century, not even the 20th century. Based on principle, I mean, I'm talking about the periscope, for example, as a visual aid. That's 19th century, and manometer. Okay, so we are executing the maneuver to rendezvous after 2 days with the space station. Now, the space station is an enormous structure. It's so impressive. You know, you're there for 2 days, and you are kind of all alone, or with your crewmates, and then you approach this tremendously large structure. It's so unexpected and so theatrical. As you say, it's bigger than a football field. It doesn't weigh very much because, again, weightlessness, it doesn't have to be very strong, but it's very big. This is the real view of it. Great complexity in terms of the different. It was built node by node, incrementally, and it's any biological system. It's kind of organically growing. This is how it looks inside. This is it's probably not the same as you expected from 2001. It's a little bit messy. It looks very much like a submarine. There are windows on the floor. It's stabilized so that it's always parallel with the Earth's surface, so it actually has to turn very slowly. It turns 1 degree every 5 minutes. So I always thought that I could feel it turning. Most of the controls, there's a manometer here on the right, again, for emergencies, in case everything else fails, but otherwise it's controlled with laptops. Laptops are great because if something fails, they just plug in a new laptop. This is the view in the other direction. This is where we have our dinners, and the food rations are on the right. Now, I'm sure you wonder what's behind those panels on the wall, like on Space Trek. There was always this question of opening up one of the panels on the wall. So there it is. That's the rat's nest. That's the space station. But don't worry about if something fails. We have excellent tools on board. And that's our toolbox. And there's plenty of tape. Duct tape of different kinds. Some of them are aerospace quality duct tape. Notice this great notion of having that white stuff, what you call it? Styrofoam, right? The styrofoam is the holder for the tools. Beautiful user interfaces. I particularly remember this one because it has modes, Larry, and you see it has this mode, the red mode and the black mode. And if you do that, well, the reason I remember it because in one of our simulations we died, and we were 3 of us, as a crew, were doing a simulation, and we were going to depressurize, and we had to set, this is one part, we had to set the alarm, and this is setting the alarm, and of course we forgot to we set the right value, but we didn't set the right mode, and we died because of that. We were given a hard time, and I felt really bad because I knew it. Okay, this is not rocket science, so I should have been able to catch that. But you can have fun, and this is how we have dinner. We got a package of fresh oranges, so that's great. This is our toilet. And as you remember, here is the panel for the control of the toilet, and not quite the instructions, but the warnings and other documentation above and below. I'm not going to bore you with it, but there's a test on this, and it's quite serious, and it's pretty similar to the one in 2001. What happens if this fails? What happens if that fails? It's really funny. The 2001 talks about problem A and problem B. It's supposed to problem 1 and problem 2, and as you notice, you can here see the number 1 is the yellow receptacle on your left, and number 2 is the white. Okay. So remember Star Wars, the garbage room. This is the garbage room of the space station, where of course there's a lot of garbage. That experiments that were finished, there's just so much space there, and of course the solid waste, which is that those shiny cylinders that are so well sealed. They contain solid human waste, and this is all waiting to be deorbited. This is actually a freighter that came up. It was unloaded. And now it's used as a garbage truck, and when it's full, it will be deorbited and burnt up in the atmosphere. Also, when we came back, our living room was also filled up with garbage, and because it was separated okay, so sorry, this one. So that's the garbage room. All right, the moon is a harsh mistress. I took it to space, and that's why I noticed again that sentence about 10 to the 8, 10 to the 8 bits. But to show you that not all of the space station looks like that, this is the American sector, and it's kind of nicely painted, and it's pretty shiny. This is the brand new segment for the European Space Agency. That wasn't there the first time I was up there. 2 years later, it was already attached, and it's pretty nice. Mike Fink is a wonderful colleague that I came back to. Now I have to show some pictures from space. So this is a picture that I took just approaching the Bay Area. We were a little bit too far to the north, but you can see very well the Bay Bridge, the Golden Gate Bridge, and San Francisco. And then looking toward the south, this is South Bay from space. Of course, this is not. I mean, with Google Earth, you can do this all the time. But it's interesting that you can, with a normal Nikon camera, actually these D3X or DX or X3 or whatever it is, D3X. You can take with a handheld 400 millimeter lens. You can take a pretty good picture. In fact, you can magnify it, and here we are. There's SLAC, and there's the stadium, and so we have somewhere here. It's a lot of fun. This is what I called fractal island, and just want to show you that nature has these repeating patterns, and being in space is very much like being in an airliner, except you are looking at different things. But in an airliner you're looking at a lake, and from space you're looking at the Mediterranean Sea, but they look the same. And look, for example, these fantastic patterns. I'm not sure about. I'm quite sure that this reminds you of something. Maybe Van Gogh. It's weird because Van Gogh is showing the sky and we are showing the Earth, but hey, it's fractal. This fractal pattern is the same. So this is the schema of coming back to landing. Here's the path of our landing as taken from a fax from the ground. We are still in the hatch, ready to board the spacecraft. This will be the acceleration on re-entry. It's a different profile than going up, but it's still not unreasonable. And here we are coming down. We are barely missing a highway and a railroad. The railroad tracks we hit pretty hard. There's this thing called the soft landing rockets. They ignite at 80 centimeters of altitude. You are going at 10 meters a second, so it's 80 milliseconds. It's an explosion, but it softens the impact. You are very comfortably ensconced, and you're exactly in the right position in a seat liner that is made to your body, and so you don't get hurt. But of course you will be dragged along on the parachutes for a while, and then here's the kind of the burnt spacecraft. The window it looks clean because it was covered by another window that was torn off when the heat shield was jettisoned. So it's so that the rescue people can look inside if everybody's all right or not. And here I am. Advice. I will just. I don't have too much time, and I really don't want to bore you. But I will say one thing that there's a book by George Polya, How to Solve It, and if you it costs peanuts, and you should buy it. And if there's a checklist in it on how to solve problems. I'm disappointed that this is not taught in classes. Because if you know this, you will get a job everywhere. Not only you will pass your GRE, but you will get a job any technical company. It's so simple, and just look at it, understanding the problem, having a checklist that have spent some time in understanding what the problem is, draw a figure, introduce suitable notation. I haven't seen any applicants yet who would give them a trivial problem and they don't understand what the problem is, they don't make a drawing, they don't introduce suitable notation, and then they screw up. for no good reason whatsoever. So if I can just give you one thing, and I should have just bought a giant bag and give one to everybody, but anyway, I didn't, and I'm sorry. But go to Amazon, look it up, how to solve it, and prosper. Thank you very much.
Would you be willing to take some questions? Thank you. That was fabulous. Charles is willing to take some questions from the audience, if there are questions in the audience. Yes, sir.
What's in the water in Hungary that produces so many people of note? You had von Neumann, for example. Polya, I think, was Polya Hungarian?
Polya was Hungarian too. I would have recommended even if you weren't. But thank you for being so kind. I don't know. I think we have lots of people there, and it's just a curve. I'm not even going to say what curve.
Other questions? Yes.
What country do you see leading the next innovations in space? Will it be the U.S.?
Well, I hope so. I think that with the commercial enterprises, I mean, when you look at SpaceX, for example, and what Amazon is, what Jeff Bezos is doing, and other private companies are doing, that innovation is amazing. And I certainly don't see it anywhere else in the world, just because the whole idea of innovation is so American to begin with. What's new is that America focuses this innovation talent to call it the problem of space. Now, also the good thing about America is that people are very pragmatic, and if it doesn't work, they're not going to do it. It's in the past, space was more of a question of, well, it's a political. It wasn't certainly profit oriented, shall we say? But as we know that it's with profit that the real growth starts, and the profit is going to come from investment and innovation, and I think it's happening. I think it's going to be U.S. I really do. Yes.
What do you think is the next frontier?
Oh, the next frontier. I mean, I don't know. I think that quantum computing. I think the biotech. I mean, the combination of biology and computer science. The brain research, for example, is incredible. Maybe we'll get AI. There's this book out called Super Intelligence that discusses some of those paths to AI. Any of those, it's figure it out. It's up to you guys.
Yeah.
You had two things. You had computers and space. What's the third thing for you?
Oh, my family. And that's the first thing, but I don't talk about it.
Other questions? Yeah.
Did you have occasion to have any debris drills in space? Is that a big concern when you're in the International Space Station? Of course, that was a major plot point of a movie last year. I'm wondering how important a problem it is.
I think it's a modest problem. We had a fair amount of training for depressurization. There are really three important things that can happen in space: toxic atmosphere, fire, and depressurization. Those are the red lights. Everything else is yellow. And of course, the depressurization can happen because of meteorites, just as well as from debris. I think it's a minor concern. Sometimes.
And my name is Jack, because I was waiting for him at his return, and during that time I spent some time with. I spent some time with very important NASA people, and they were telling me that they had to move the space station a little bit up because there was some debris from a Spanish satellite, and apparently they keep doing this on a daily basis. So it very much is a problem, and a space station can take something this size, but it can't take this. Okay.
I kind of thought that was one you might get a different point of view on from the wife, but
I appreciate that. Thank you. But I stand corrected. Yes.
yeah, go ahead.
Could you comment on von Braun's plan to go to Mars and how that might differ from current thinking?
Yes, I went through that slide. There were a couple of things about it. One of them is it involved nuclear engines from orbit, not to go to. He would have used a lot of Saturn V, actually kind of a simpler version of Saturn V's to lift the weight to orbit, which is, by the way, an infinitely better way of again using unmanned rockets to put cargo into space. Using manned rockets to carry cargo is crazy. But anyway, it's neither here nor there. So he would have put a lot of cargo into orbit, and some of those would have been nuclear, very high impulse engines. It's he would have restarted NERVA and used the nuclear engines. I think all the other details are pretty clear. What he didn't take into account is that probably the radiation, not from the nuclear engines, but from the space, would have been a little bit higher. But maybe that's included because of the nuclear engine, because you need to shield for that. So you probably could have shielded for the other one too. It's interesting that his spacecraft, 6 people would have gone to Mars, and I don't remember how many would have landed, but from out to Mars it would have been 6. And the spacecrafts were rotating. So he did consider the question of long-term weightlessness. But by and large, I think that it was a very realistic in technical terms. Now again, the question of cost, the question of why, and the question of nuclear, and his unfortunate death, early death, is. It's all conspired against that.
We have a very patient.
Sorry.
Do you have any other books that you would recommend besides the ones you mentioned?
Good question. I will think about it and I'll come back to you. Yes, I do. It's if you're interested in the history of science. My dad has the best book on history of science that we edited. It's now available in English. So if you look for the cultural history of science on Amazon, you will get my dad's book, and I recommend it incredibly highly because it's very, very interesting. A whole generation of maybe it's not the water, maybe it's a generation of engineers in Hungary grew up on that book, and it will tell you everything you wanted to know about Kepler and things that you don't usually find.
I think we have time for one last question, if there's one last question. I'll let you choose.
Have you happened to read The Martian by Andy Weir, written out in Livermore?
I did not.
He talks about a person stranded on Mars, part of the first Martian mission, but his concept is this constantly orbiting spacecraft between Mars and Earth that keeps going like this. And you hit your right on and you get off.
Well, I can only say what von Braun and I think he thought a lot about it. I'm sorry, but
Not a question. Köszönöm szépen.
oh, nagyon szívesen. It's a Hungarian thank you.
Well, I would like to thank you for a fascinating evening and for being one of our heroes. Thank you very much.
Thank you.